How is it that we can make our Tesla coils reach the next level in performance? I'm going to show you how to tune the resonant frequencies of the primary and secondary coils of your Tesla coil so that they can resonate together and therefore increase the overall performance. I'll also show you some tips and tricks you can use if you don't have all the necessary lab equipment to do this. The effectiveness of your Tesla coil depends on the ability of your primary coil to resonate at the same frequency as your secondary coil. But why is this the case? Well, in a normal transformer, energy transfer between the primary and secondary is achieved because the iron in the core guides the magnetic field, keeping it locked in place. However, in a Tesla coil, we have no core. Therefore, we make them resonate together at the same frequency. All things which are resonating at the same frequency will share energy. It's like that saying, birds of a feather flock together. But resonance has even more benefits for the Tesla coil, but more on that later. So how do we even start to design our Tesla coil? Well, our first goal is to find the resonant frequency of our secondary coil plus top load and then design the primary to match it. We start with the secondary because it is the heart of the Tesla coil and it will determine everything else. So how do we design our secondary coil? Well, if you have a particular frequency in mind, then you first need to find the inductance and capacitance of the coil. The inductance is easy, just use the equation for a long solenoid. However, the capacitance is made up of the interturn capacitance, top load and ground capacitances and is actually very difficult to calculate. But fear not, the lovely chaps over at gorechillin.com have made a surprisingly accurate online calculator for you. You enter the length of the coil, the diameter, the number of turns, and whether you have a top load or not. It even calculates the capacitance of the top load for you, giving the option of a torus or sphere. The link is in the description. If you lost count of the number of turns while winding your coil, simply divide the length of the coil by the wire thickness to estimate the number of turns. To form the coil, you can use cardboard or plastic tube. Usually I use these offcuts of old sewer pipes which thankfully have never been used. You can make all sorts of different Tesla coils for your experimentations. When winding your Tesla coil, it's important to remember these points. If you increase the number of turns, the diameter, length of the coil, or size of the top load, the resonant frequency will go down. In general, large Tesla coils end up somewhere around 100 to 300 kilohertz range, and tiny Tesla coils can make it up to the 2 or even 3 megahertz range. Now beware of this. Tesla coils can be extremely powerful radio emitters. They can disrupt your neighbor's electronics, and that's illegal in most countries. In my case, my 1.2 megahertz Tesla coil actually sets off the electronic doorbell. Before I discovered this was happening, I actually thought the neighbor was playing tricks on me. To avoid this, make sure that the wavelength of your Tesla coil is much bigger than the physical size of it. Then it will be a poor radio emitter. So how do we make our top load? Well, there are several ways. To make the top load, I use this old tin can. These are good because they're easy to solder to. Another trick is to use an old Christmas tree bauble and cover it with metal sheet. Some people also use metallic ducting and stretch it out into a toroid shape. If you want, you can always steal your mom's frying pan and put that on the top. By the way, hiring and lowering the top load allows you to fine-tune the resonant frequency if that's what you require. If your goal is breakout and sparks, something pointy will help you to get the spark at lower voltages. In this case, a top load can have the effect that, acting as a capacitance, it stores energy such that when the breakout occurs, that energy is released, making the sparks look thicker, whiter and louder. And this is why resonance is so important for your Tesla coil. The more it can resonate, the more energy it will store, the more energy it can release. The bigger your sparks will be, which will impress your girlfriend and scare your mom. But what is the best configuration if you're interested in wireless power? Well, in this case you should have a top load, but not too big. Spherical is best, no sparks, and a good earth connection. Resonance in the Tesla coil means it will be more effective at sending current pulses into the earth, which is vital in Tesla's method of wireless power. Of course, the quality factor is also important here, but that's beyond the scope of this video. So how do we check the resonant frequency of our coil once we've wound it and attached our top load? Well, there are several easy methods. You can connect it in series with a 10K resistor and function generator like this. Then place your scope probe near the end and scan the frequencies using your function generator. The resonant frequency will show up as maximum amplitude on the scope. But what if you have no function generator? If you don't have a function generator, then simply wind a few turns on a primary and connect the circuit I show here. This will automatically oscillate at the resonant frequency and then just measure it with your oscilloscope. This works with most transistors. Just use a low voltage for the power supply. By the way, I explained and showed a proper working circuit example of this type in a previous video which I'll link above. What about if you don't have an oscilloscope or a function generator? Well, in this case, you can still measure it if you have a digital voltmeter which can count frequency. Just connect it across the base and the emitter of the transistor. Simple. Just make sure the power supply is at a low voltage when you make these measurements. Just remember, extraneous objects near the Tesla coil and streamers can change the resonant frequency. So try to measure it in the place where you intend to use it. Now that we have our main coil and top load, how do we design our primary coil? Well, since we know our resonant frequency, this equation will tell us the inductance and capacitance we need to get to. To begin with, simply choose a preliminary value of capacitance, which you can change later, then calculate your inductance. Then use the equation of a solenoid to find the height, diameter and turns of your primary coil. Or if you're lazy like me, you can use an online calculator. I'll leave some links in the description. Now, something important about the primary coil. If you put the capacitor in series with the inductor, this will help because the capacitor will block DC and low frequency currents, preventing a short circuit in your primary. Obviously, this only works with the half bridge and full bridge topologies though. With these drivers, if the primary is resonating and you're driving at the resonant frequency, you should automatically achieve some zero voltage switching. But to help facilitate this, place some small capacitors and diodes in parallel with your switches. Now keep this in mind if you don't want to blow up your switches. If you make your primary coil inductance too small, it will be a very small impedance and pull large peak currents, which could damage your switches, especially if you're using main voltages, so consider that when you're designing it. I recommend you keep your primary winding low, near the bottom end of the coil. This will keep the coupling between the two coils low. Low coupling allows the secondary to perform its function as a resonator more easily, meaning you will get more voltage for less power. I hope you found this video useful and maybe learned something. If you would like to help the channel, you can do so using the links below or simply clicking the like button. Thanks a lot. See you later.